Okay, so now it's my turn, and my Korean is as bad as Nicholas, so I will also have to do my presentation in English, but Professor Lee will help with a bit of translation where it's needed, and I'll just, after each slide, see if there are any comments. So quickly to introduce myself, Peter Wulf-Anderson. I have an engineering degree in acoustics, and I'm also the co-founder and owner of GRAS Sound and Vibration. Let me see. So this is a brief agenda of what I will go through. There will be a little bit about the theoretical part, what happens when you put a human body and ear canals in the sound field. Something about the different types of headphone, in-ear, on-ear, over-ear. Something about the ear reference points. When you work with ear simulators, you have to take into account where you are referencing. And also a bit about the many international standards covering the artificial ears and headphones. After that, I will talk about the actual, you could say, test you have to do on the headphones, and a little bit on how to do it, and also some of the other tests that are not so basic. And last, I will present some of the, you could say, new developments we have done in this field, new ear simulators that can help you in your design process when doing headphones. So, definitions and abbreviations. If we take one step back and say ear simulator and coupler history. In the old days, there were no ear simulators. You have to use the human ear to do listening tests. Of course, that is not as scientific, precise, because each human being will listen a little bit different to the pair of headphones. So there was a need for some kind of device that could translate the acoustic signal into some electrical signal that could be analyzed. And the first ear coupler was designed back in about 1920, about 100 years ago. But the first standardized coupler came out many years later, and actually almost 60, 70 years ago, the first standardized coupler was released to the market. But we could ask the question, why do we actually need these ear simulators? Why can't we just use a microphone to record the signal from a headphone? It has to do with when you put a person in the sound field change. It's not the same as just having no person there. So the person, the head, the torso, the pinna, the ear will start changing the sound. So it's not the same as just measuring with a microphone. If we look at what happens when the sound enters the ear, it enters into a smaller volume, as we see here by a box, and you have a small speaker being the headphone. And that has a very different acoustic impedance compared to normal free field condition. And on the schematic on the right over here, we have a free field response being, you could say, like a flat line over frequency. But if we look at the impedance that we look into here at the ear canal, it looks very different from free field. Not nearly anything that looks like a flat response.
우리가 이어 시뮬레이터라든지 이런 마이크로폰이 일반적으로 우리가 스피커 측정할 때 쓰는 마이크로폰하고 뭐가 다를까에 대해서 이제 좀 살펴봐야 되는데요. 이제 그 이어폰 헤드폰들이 일반적으로 보면 고막을 이렇게 막고 맞고 듣는 것들이 일반적으로 다릅니다. 그러면 그게 왜 다르냐고 하면 일반적으로 스피커에서 나오는 시그널은 3차원적으로 퍼져나가죠. 그렇죠? 그렇게 해서 우리가 고막으로 듣는 걸 갖다가 프리필드 조건에서 듣는다고 보시면 돼요. 자유음장 조건에서. 그러니까 자유롭게 음이 3차원 공간으로 퍼져나가서 듣는 거하고요. 여기서 이제 이어폰, 특히 이제 이어폰, 헤드폰 같은 경우에는 스피커가 저기서 나오는 것처럼 스피커가 있는데 마이크로폰 위치가 마이크로폰이 있고 그게 이제 관으로 막고 듣는 거죠. 여러분도 아시겠지만 똑같은 소리도 제가 이렇게 말하는 소리를 만약에 파이프로 이렇게 퍼져나가지 않게 해가지고 고막에다가 바로 대면 전혀 다른 소리로 들리고 엄청나게 큰 저음이 들릴 겁니다. 예, 이제 그런 상황에서 측정해야 될 마이크로폰들은 전혀 다른 특성을 가져야 됩니다. 그게 바로 커플러가 되고 이어 시뮬레이터가 되는 겁니다. 그래서 그냥 우리가 그 스피커 되는 마이크로폰을 그냥 여기다가 이렇게 뭐 이게 통에다가 끼워가지고 이렇게 재면 되는 거 아닌가 단순하게 그렇게 생각할 수 있는데 전혀 그렇지가 않습니다. 예. 그래서 그 부분에 대해서 지금 이야기하는 거고요. 그래서 주파수 특성 자체도 완전히 이렇게 달라진다라는 거예요.
Okay. So if we look at the whole, you could say, the whole head, torso, body influence on the sound field, I have here two, you could say, different scenarios. One where we just use a microphone to pick up the response of any sound. In this case, we just have a speaker. And let's say we have a perfect speaker with a perfectly flat response. And we use a perfect GRAS microphone. What we would get would be, again, just a flat response. Free field measurement of a flat response. But if we make a similar measurement with a head and torso simulator, and we record what comes into the eardrum, the result is very different. We can see there's a big peak up here in the mid-frequency range, around 1 to 5 kilohertz. We have a big raise in the sound due to the effect of head, pinna, torso, ear canal, eardrum, and everything.
지금 완벽하게 그 평탄하게 나오는 그 스피커를 완벽하게 평탄하게 나오는 그 측정을 할 수 있는 마이크로폰을 통해서 예를 들면 수미터에서 떨어뜨리고 어떤 반사음도 존재하지 않은 무향실에서 만약에 측정하게 된다면 위에 같은 조건에서는 주파수 특성이 이렇게 플랫하게 이렇게 나옵니다. 그런데 똑같은 조건에서 이제 그 평탄했던 마이크로폰을 사람 모양으로 생긴 저기 마네킹에다가 고막 위치에다가 예를 들면 이렇게 쑤셔 넣어 가지고 잰다면 위에 파란 컵으로 나오겠죠. 왜냐 그러면 여러분도 알다시피 이게 고막이라는 게 자세히 보면 한 2.5cm 안쪽으로 들어가 있거든요. 마이크로폰에다가 앞에다가 이상한 구조물을 달아놓고 이렇게 옆에다가 뭐 많다로 놓고 하면 당연히 주파수 특성이 바뀌게 되겠죠. 이제 사람 모양으로 하면 저렇게 3kHz 부근이 이렇게 붕 솟은 이런 특성으로 반드시 가져야 됩니다. 다른 말로 하면 나중에 저 스피커를 나중에 이어폰, 헤드폰이라고 본다고 하면 반드시 이런 파란 모양으로 가야 원래 저기 굉장히 훌륭한 스피커의 소리를 못 하게 되겠죠. 그래서 이어폰, 헤드폰은 나중에 고막 위치에서 재면 절대 플랫하게 나오면 안 되고요. 이 파란색 모양으로 가는 게 우리가 사람이 느끼는 플랫하다는 스피커로 이어폰으로 느끼게 되어 있습니다.
So if we try to break down the head-related transfer function, meaning the sound coming from here entering into the ear, we have the total was, as you saw on the other one, the blue line here. That was the total, you could say, transfer from free field to eardrum. But it consists of, you could say, two different contributions. The green dotted line here is the effect of the actual physical body. Again, the head, torso, and the pinna. And the red curve being what happens when the sound enters the ear canal and has to go all the way into the eardrum. So the complete head-related transfer function is a sum of the green line and the red line. So it's a sum of the, you could say, physical appearance and the transfer function in the ear canal.
아까 보여준 그 커브가 파란색 커브였고요. 저렇게 나오는 걸 좀 더 구분해서 본다고 하면 빨간색하고 이렇게 연두색 두 개로 이렇게 볼 수 있는데요. 연두색 같은 경우에는 스피커가 아까 이 평탄한 이상적인 스피커가 모양새에서 여기 조건은 정면에 있다는 가정입니다. 바로 내 앞에서 1m 앞에서 스피커가 있는 경우 올 때 어디까지 반영하느냐 그러면 내 몸통, 머리, 그다음에 귓바퀴까지 특성만 본다고 하면 연두색이 나오고요. 그때 같은 경우에는 한 6km 정도가 이렇게 붕 솟는 형태로 나오고 9km가 쑥 꺼지는 형태로 나옵니다. 예. 그러니까 예를 든다면 마이크로폰을 깊이 안 넣어놓고 만약에 여기 내가 이게 귓구녕 바로 웨이도 입구에다가 마이크로폰을 놨다고 하면 바로 저런 연두색 커브가 나왔겠죠. 그런데 마이크로폰이 크게 있지 않고 사람의 고막은 더 안쪽에 들어가 있죠. 한 2.5cm 안으로 들어가 있는데 그러면 여기 웨이도 입구에서부터 고막까지 특성을 본 게 바로 빨간색 그래프입니다. 이게 이제 안쪽으로 들어가 가지고 있고 한쪽이 뚫려 있고 한쪽이 막혀 있는 반파장 공진이 나오기 때문에 4분의 1 파장 공진되는 저기 3kHz 부근이 뜨고요. 그게 대한 또 3배 높은 12kHz가 붕 뜨는 형태로 나옵니다. 이 두 가지가 같이 이제 결합돼서 보면 아까처럼 파란색 저 그래프가 나오게 되고 저렇게 들리면 사람들은 소리가 내 앞에 있구나 이렇게 느끼게 돼 있습니다. 평탄한 스피커에서 나오는 소리 이미지가 앞에 있네 이렇게 느끼게 돼 있습니다.
Also, when you talk about head-related transfer function, you can either talk about the, you could say, 0 degree, where you have the sound coming in from the front to the head, or you can talk about the diffuse field head-related transfer function. The reason for the diffuse field is that normally when you have a listening experience, you also have a lot of reflections from walls, from back. So it's not usually just you could say, sound coming only from one direction. You have reflections of walls. So you could say, have a more realistic transfer function when you design headphones, you often talk about the diffuse field head-related transfer function. And there are small differences, as you can see on the blue and the red curve here. The blue being the free field and the red one being the diffuse field.
여기 보면 HRTF는 머리 전달 함수라고 그래가지고 있잖아요. 각각의 방향별로 오는 사람이 밤에 이렇게 눈을 감고 소리가 오는 방향을 찾는 메커니즘이 HRTF라고 해서 우리말로 하면 머리 전달 함수고요. 그래서 각각의 음색하고 양기에 도달하는 시간차, 크기차, 음색이 다 다르기 때문에 우리가 눈이 없더라도 귀 두 개만 가지고도 찾는 원리가 HRTF에 있습니다. 이게 DRP라는 것들은 바로 이제 드럼 레퍼런스 포인트 그래가지고 고막의 위치에서 재는 거예요. 우리가 인이어 이어폰, 커널 이어폰을 꼈을 때 이 삽입되는 깊이를 일반적으로 DRP라고 일반적으로 이야기를 하죠. 실제로 간에까지 할 수는 없지만 이제 보청기 시대 때 나온 거라서요. 그 다음에 프리필드 같은 경우에는 아까 얘기해서 0도에서 바로 자기 정면에서만 오는 소리를 모사하는 겁니다. 나의 모든 관심사는 0도 앞에서 오는 소리밖에 없다. 무향실이니까 반사가 없으니까 당연히 0도만 있었겠죠. 그게 이제 프리필드고요. 갑자기 디퓨즈 필드가 나왔는데 실제로 이제 우리가 듣는 이렇게 청실 공간은 물론 스피커가 앞에 있기는 하지만 정면으로 오는 소리부터 해가지고 옆으로 맞는 소리, 바닥 맞는 소리, 천정, 후면 맞는 소리가 모두 더해지기 때문에 실제로 우리가 실내 음향을 다룰 때는 프리필드라고 가정을 하지 않고 모든 걸 디퓨즈 필드를 가정을 해서 계산을 하게 되어 있습니다. 단지 흡음률이 조금 좀 다르다라는 그런 가정이죠. 하지만 모든 방향에서 소리가 온다. 그게 바로 디퓨즈 필드이고요. 이 디퓨즈 필드는 이제 흡음률이 고려되지 않은 모든 방향에서 동일한 흡음률이라고 가정했을 때 모든 방향에서 오는 에너지가 동일하다고 가정해서 나온 그래프가 바로 빨간색 디퓨즈 필드 그래프입니다. 정면만 올 때는 파란색이고요. 차이가 보면 3kHz에서 차이가 있고요. 재밌는 차이는 7km에서 8km 정도 보면요. 정면으로 올 때는 쑥 꺼져야 되는데 모든 방향에서 오면 쑥 솟게 돼 있죠. 8km가 그렇죠. 이 굉장히 중요한 차이입니다. 나중에 이어폰 튜닝을 할 때 3kg하고 6kg, 7kg를 어떤 식으로 내가 튜닝할 거냐에 따라서 좀 이미징을 좀 앞으로 가게 할 거냐, 아니면 좀 음악적으로 듣게 할 거냐의 차이가 있습니다. 네. 오케이.
So also just to you could say briefly explain what is the difference between ear couplers and ear simulators. People often use ear simulators, ear couplers, they talk about the same thing. But there are actually in the standards a small difference. Ear couplers are typically, you could say, very simple couplers that are just a single volume represented in electrical model as just a capacitor, typically have a very, you could say, linear frequency response, where ear simulators are, you could say, more complex models of the human ear, also taking into account the eardrum effect and the inner ear parts, and they have much more complex, you could say, electronic equivalent models of both coils, capacitance, and resistance.
이어 커플러가 나오고 이어 시뮬레이터가 나오는데요. 이어 커플러는 아까 맞고 듣는 거라지 않습니까? 그러니까 맞고 듣기 때문에 어떤 최적이 만들어지겠죠. 그 최적의 양만 맞춰주는 겁니다. 그래서 그 커널형 이어폰을 들을 때는 쑥 깊이 들어가 있으니까 뭐 최적이 2cc밖에 안 된다. 위에 올리는 것들은 뭐 4cc가 될 수도 있고요. 위에서 하면 6cc가 나오고 좀 더 큰 거는 8cc가 나온다든지 그런 식으로 해서 다양한 최적만 맞춰주는 거고요. 정기적인 등가에서 보면 커패시터의 성격을 갖게 되겠죠. 그 다음에 이어 시뮬레이터는 그것뿐만이 아니고 실제로 이제 시뮬레이터니까 모사해야 되겠죠. 기의 특성을 좀 더 모사해서 굉장히 사람이 귀라는 게 이제 그 웨이만 있는 게 아니고 중이 있고 내이가 다 있지 않습니까? 고막 뒤에도 또 공간이 있습니다. 이런 복잡한 어떤 귀의 특성을 갖다가 모사하기 위해서, 이제 즉 모사한다는 말이 임피던스를 모사하게 되겠죠. 임피던스를 모사하기 위해서 굉장히 좀 복잡하게 만든 게 이어 시뮬레이터고, 그게 좀 더 실제 이어폰, 헤드폰 측정할 때는 더 가깝습니다.
Okay, so different types of headphones. Again, just so you know, because I will be using some of these terms in my presentations later. We have what we call the circum-all headphones, are the big ones that covers your ear, also called over-the-ear headphones. We have the super-all headphones that are smaller and sits on the ear, also called on-the-ear headphones. We have the earbuds that are little tiny ones that sits right at the, you could say, ear entrance point, not all the way in the ear canal. And the last one are the ones that we push all the way into the ear canal. And they have these different, you could say, CA, SA, EP, and IE shorts, which you will see during my presentation. Also, we have reference points in the ear. We do refer to different reference points. The first one is out here, you could say, in the open part of the ear, not right where the ear canal starts, but a little further out in the concha. And that's called the ear reference points, and are typically used with ear simulators or ear couplers that are meant for the on-ear and over-ear headphones, or circum-all and super-all. Ear entrance point is right where the ear canal starts, so right here where the ear canal is, and again that's the reference point for the coupler you need for the earbuds. And the last one is drum reference point, drum referring to the eardrum. And if you are measuring headphones or earphones that are going into the ear canal, you need to use ear simulators that has drum reference point.
지금 그 세 가지 포인트가 있는데요. 고막의 위치는 똑같겠죠. 중요한 거는 스피커의 위치가 어디로 이제 잡힌다는 건데, 서큐모랄하고 그 다음에 수프라오랄 같은 경우에는 조금 눌러지겠죠, 그렇죠? 그게 이제 이어 레퍼런스 포인트, 우리 통화할 때 정도 이렇게 올라가 있는 여기 스피커 리시버가 위치하는 위치 정도로 보면 될 것 같고요. 이어 엔트런스 포인트는 우리가 이어버드 타입 있지 않습니까? 우리 뭐 일반적으로 옛날에 우리의 오픈 타입의 이어폰들이 했을 때 유닛이 작용하는 위치, 그 다음에 제일 사실 논란거리가 드럼 레퍼런스 포인트인데, 이게 이제 커널 이어폰이 이제 쑥 들어가지 않습니까? 이제 위치인데, 실제로는 드럼 레퍼런스 포인트까지 들어가지 않습니다. 드럼 레퍼런스 포인트라는 게 고막에서 1cm 앞이거든요. 그렇게 하려면 적어도 3단 팁을 갖다가 귓구녕이 굉장히 넓으신 분들의 3단 팁으로 쑥 밀어 넣어가지고 할 때 들어가는 정도가 드럼 레퍼런스 포인트인데, 거기까지는 실제로는 못 쓰죠. 예, 그런 유닛의 위치에 따라서 ERP, EEP, DRP 이 세 가지가 있습니다.
Okay, also standards. There are, you could say, many different standards covering the whole headphone industry. I will focus in my presentation on the standard that covers the equipment we do, meaning the ear simulators and ear couplers, and that's the one here in the middle, the 6318. And that standard today covers all the ear simulators and ear couplers. In the previous, or you could say earlier on, there were several different standards that covered different types of ear couplers and ear simulators. But today, the 318 standard includes all the available ear couplers and ear simulators today, ranging from the 318 coupler, the 1-1, typically referred to as the 318 because it was the first one in the standard. There's the 6cc coupler, which is a simple large volume coupler. There's the what we normally would call a 711 coupler because it used to be covered by a standard called IEC 6711, but now it's a 318-4 coupler, and so on. And that you can see all these numbers refer to different types. The last one is the hats and head and torso simulator, and we have our version over here. We only have the head with us today. The torso was too big to transport, but these are all covered by international standards today.
국제 기준들이 전 페이지도 왔지만 여러 개가 옛날에 난립을 했었는데요. IC에서 60318로 다 해쳐 모여 해가지고 좀 다 모였습니다. 그래서 1부터 해가지고 7까지 이렇게 나오게 됐고요. 지금 우리가 많이 쓰는 것 같은 경우에는 1도 있고요. 그 다음에 이제 6cc 커플러도 있고요. 그 다음에 이제 많이 쓰는 건 4죠. 4. 711 커플러라고 그래가지고 지금 이어폰 잴 때 대부분 쓰고 있습니다. 그 다음에 이제 7이 이제 그거는 안에 있는 귀 속 안의 특성뿐만이 아니고 바깥에 있는 귓바퀴부터 몸통까지 이런 것들 다 모사한 게 이제 7로 해가지고 이제 해체에 대한 규격이 정해져 있습니다. 그래서 1, 4, 7 이건 저희들이 이제 많이 알아야 되는 부분들인 것 같습니다.
Here is just mentioned a few of the other standards that are also, you could say, sometimes interesting in this business. I will not go into details, but I just mentioned them so you know they are also around. Typically, the most common standards are the IEC ones. So we now covered what we call acoustic diffraction. That is putting the physical person in the sound field. And we talked about acoustic impedance, or transfer impedance is typically what we use. Transfer impedance meaning the transfer from the sound source to the eardrum. And these devices, you could say the ear simulators and mannequins, are great complements to the human ear. But we cannot rely 100% on just doing measurements. We still need to do a listening test in order to make sure that the sound we get is also the sound we like to listen to. But the ear couplers, ear simulators, and head and torso simulators are very good for doing your measurements and trying to change characteristics of your headphone and do another measurement. And then in the end, you need to also do some personal listening tests.
Would you speak more louder? More louder.
More louder.
Yeah.
Okay, sorry. I will.
지금 여기 선을 그어놨고요. 선을 그어놔서 이제 왼쪽 이게 이제 음향적인 회절 현상을 모사를 해야 됩니다. 예. 그래서 귓바퀴가 굉장히 중요하고요. 이제 귀의 형상 같은 게 굉장히 중요하겠죠. 사람하고 최대한 가깝게 하는 연구들은 이쪽에 있고요. 이제 오른쪽 파트에 있는 게 이제 음향 임피던스로 가지고 맞춰주는 겁니다. 예. 맞춰줘서 실제 고막에서 응답을 똑같이 이제 모산하는 거겠죠. 그리고 두 개가 접근 방법이 약간 다른 거고요. 이 두 가지가 결합되어 있는 게 우리가 이제 실제로 쓰고 있는 제품들이겠죠. 근데 잘 보면 우리가 사실 이어폰, 헤드폰 이런 거 할 때는 왼쪽에 있는 어쿠스틱 디프렉션은 별로 중요하지가 않습니다. 어쨌든 맞고 이렇게 듣기 때문에 오른쪽이 훨씬 더 중요하죠. 그래서 오른쪽 있는 게 우리가 주로 더 많이 사용하는 부분들입니다. 예.
Okay, I hope you hear me better now with the microphone a little closer. So, next part of my presentation is about actual, you could say, headphone testing. So, what data do you need to capture when you test a headphone? Of course, the first thing would be to do the frequency response. Make sure you have a good frequency response from at least 20 hertz up to 20 kilohertz, or maybe even higher. Distortion, very important also, because human ears are very sensitive to distortion, and you need to be sure that the harmonic distortion is kept at a very low level. Also, you need to do tests for any little defects in the driver in your headphone, the rub and bus, where you test for loose particles or grinding parts inside the driver. And again, these can be noises that are far away from the fundamental, meaning the actual tone creating the noise, and therefore can be very easy to detect by the ear. Also, the dynamic range of your headphone is important. How, you could say, loud can they play? And here we often talk both about, you could say, when do they break, the destructive part, but also the non-destructive, how high can you actually play music and still get a good listening experience, meaning the harmonic distortion or the distortion should be kept at a reasonable level. I mentioned 10% here, it might be too high, but again, that's up for you could say up to you to decide how much distortion do you allow at the maximum listening level. Also what we call tracking and wiring, meaning is the right channel going to your right ear, meaning they are not reversed during production, and also that the balance between the two drivers, right and left, are kept at a, you could say, reasonably close level, so the stereo perspective is not moving because of different sensitivity of the drivers. And last, also make sure that crosstalk is kept low, so what goes to the right channel is not being heard on the left channel. At least it should be much, much lower. So these are the basic parameters you need to measure when you design headphones. Sorry, what happened there? Okay, next one. There are a few other measurements that can be interesting to do. Today, modern headphones also include things like noise cancelling circuits, and these noise cancelling circuits could also be used to, you could say, protect your ear. But if you start stating in your material that these are also kind of a hearing protection device because of the noise cancelling circuit, you have to be aware that in some countries you have to, you could say, state special numbers for that, the noise reduction factors. And there can be legislation in different countries that requires you to do that if you quote them as also being hearing protection devices. Also, another thing that is interesting to measure is leakage. If you produce headphones that are supposed to be used out in the public, it's also important that they don't make too much noise for the surroundings. Because if you are wearing your headphones on the train, in the street, in the public space in general, it's important that you do not disturb all the other people around you with your music. So there should be some kind of isolation in your headphones. It's quite easy to measure because you can just do, you could say, a measurement with a microphone and measure the, you could say, ambient noise pressure without any music to the headphones. And then you can do the, you could say, similar measurement with pink noise played in the headphones at a fairly normal, loud listening level. And then again, measure with the same microphone how much of the noise you play in the headphones are actually leaking to the outside. So now you have, you could say, noise pollution that your headphone generate, and then you can decide whether it is too much or whether it's an okay level that can be accepted by the people around you.
지금 어쨌든 이게 개인적인 오디오인데 실제로 보면 소리라는 것들은 스피커라는 것들은 50%는 소리를 앞으로 내면 50%는 뒤로 내게 돼 있거든요. 그래서 뒤를 다 이제 차단시킬 경우도 있지만 클로즈드 타입 이어폰이 아닌 이상은 대부분 다 바깥으로 소리가 많이 나가지 않습니까? 나머지 50%가 영향을 미치기 때문에 이제 그걸 재기 위해서 이제 얼마만큼 소리를 내주는 이제 재는 방법이 있는데요. 이제 그걸 지금 이게 강사분께서 이걸 왜 이 부분을 얘기를 많이 하냐 그러면 요게 재는 게 그렇게 쉽지가 않았던 게 예를 들면 헤드폰을 예를 든다고 하면 기존에 나와 있는 이 귓바퀴가 사람 귀를 모사하지를 못했습니다. 사람 귀보다 훨씬 딱딱했거든요. 그래서 실제로 우리가 듣는 것보다 훨씬 더 많은 그 양들이 실제로 재보면 이런 계측 결과 보면 노이즈가 더 많이 나오는 것처럼 다 이렇게 결과가 나왔죠. 그래서 이제 지금은 나중에 이야기가 나오겠지만 좀 더 사람 귀하고 이렇게 쇼어 경도라 그래가지고 눌렀을 때 이렇게 펴지는 힘이 있지 않습니까? 이걸 지금 좀 더 사람하고 가까운 걸로 만들어서 지금 좀 더 정확하게 이런 ANC 측정이라든지 외부로 방사되는 소음의 측정을 좀 더 정확하게 할 수 있다라는 그런 내용입니다.
Another important parameter when you design your headphone is to make a headphone which is, you could say, will give as most people a good listening experience as possible. Because we all have, you could say, different head shapes and different, you could say, shapes on the side where you have to get a good ceiling. It's important in your design process to make sure that your headphone will fit as many people as possible and give them a good listening experience. Even when you move the driver in front of the ear canal, that also changes the sound field. So the better you can design your headphone to be immune to different positioning, different, you could say, leaks, the more people will like your headphone. So trying to do a test where you move the headphone around and look at the change in response, and the smaller changes you have in the response by moving the headphone around, the better the design of the headphone is for as many, you could say, customers as possible.
예, 여기 보면 아까 HRTF 이야기했는데 HRTF는 사람마다 다 다르죠. 근데 우리가 이제 측정하는 목적에 비해서 사람에 대한 특성들을 갖다가 표준화되어 있는 여러 사람을 평균을 해가지고 표준화되어 있는 이제 키마라고 하는 어떤 그 장비를 표준 더미 헤드를 이제 그라스에는 만들게 됐고요. 이제 그걸로 가지고 기본적으로 측정을 하는데 중요한 거는 이제 10kHz 이상 같은 경우에는 어떻게 착용했는지에 따라서 특성이 워낙에 크게 차이가 나기 때문에 헤드폰 측정할 때는 그 보편적인 특성을 보려면 한 번째 가지고는 보편 특성을 볼 수가 없고요. 한 10번 정도 반복 측정을 해가지고 끼고 측정하고, 그래 일반적으로 보면 아이디얼로 해가지고 자기가 제일 편한 상태를 한번 측정을 하고요. 조금 내가 생각이 좀 위로 올라가는 거, 좀 뒤로, 좀 앞으로, 좀 밑으로 이렇게 측정을 하고 다시 한번 또 내가 착용하기 좀 편한 상태로 해가지고 이렇게 계속 반복 측정을 해서 10번을 하면 전체 어떤 공통적인 보편적인 특성을 가질 수 있다고 하는 내용입니다.
I talked briefly about sealing. We know that both for the big phones but also for the in-ear phones, if you do not have a good sealing, the low frequency response, the bass, will be quite poor. So normally when we wear headphones, we will try to position the headphone or in the ear to make sure we have a good seal so we can hear all the deep notes, the bass tones. But when you do measurements on a mannequin like this one, we cannot hear that directly. So how can we make sure we have a good seal when we put our headphone on something like this? When we mount the headphone here, how do we make sure we have good sealing? There's a few ways of doing that. One could be in time domain. If you play a square wave through the headphones, fairly low frequency, like 80 Hertz, could be a good choice. And if you look at the output of the headphone, if the output is not something that looks like a square wave, if it's very rounded on the edges, looks more like a sine wave, that means you have, you could say, poor sealing. It should be close to a square wave coming out again. Another way of doing it could be in the frequency domain, meaning you look at the spectrum, you play pink noise to the earphones or headphones, and you then look at the response on your analyzer and say, do I get a good low frequency response? Do I get what I expect at low frequency? Or is it rolling off very much? Then you can again move the headphone around or twiggle it a little bit in the ear and make sure you have good sealing. The last thing I suggest is to listen to it, but in this case I don't mean to listen to the, you could say, the headphones mounted on the mannequin, but you could listen to the signal that the head and torso simulator is listening to. So if you listen at the output, many analyzers allow you to do that. If it's audio analyzers, they allow you to take out the measured signal and you can put a headphone on, another pair of headphones, and then you move around the headphone over here. So you can move the headphone around until you have good sealing and then listen to it at the same time. So that is another way of doing it.
이어폰, 헤드폰 뭐 측정도 마찬가지고 들을 때 제일 큰 문제가 왼쪽 오른쪽에 리키지가 생기는 부분이에요. 리키지가 생겨버리면 갑자기 아까 폐쇄장이 갑자기 프리필더로 바뀌어져 버리고 저음 특성이 완전히 다 빠져버리거든요. 그러니까 측정할 때 그 굉장히 이제 잘못된 결과를 많이 우려낼 수 있기 때문에 제일 중요한 거는 씌우고 나면 반드시 저음 특성이 어떻게 나오는지를 확인하는 겁니다. 세 가지 방법이 있는데요. 첫 번째로는 80Hz 사각파를 넣고 이렇게 봐서 파형이 제대로 나오는지 보는 방법이 있고요. 두 번째는 이제 핑크 노이즈를 넣어가지고 이제 주파수 분석을 해서 이 저음이 잘 나오는지 그리고 LR이 동일하게 잘 나오는지 이렇게 확인하는 방식이고, 세 번째는 나는 들어서 확인하는 방법이 있습니다. 그러니까 여기서 키마에서 나오는 그 레프트 라이트 녹음된 응답을 다른 이어폰으로 해가지고 다시 들어보는 거죠. 저기가 제대로 장착이 제대로 됐는지. 근데 듣는 이어폰이 실링이 또 잘 돼 있어야 되겠죠. 그 이야기는 제대로 됐는데 내가 듣는 이어폰도 잘못 착용을 해버리면 이게 그때 골 때리기 때문에. 그래서 뭐 세 가지 방법이 있는데 주로 많이 쓰는 방법은 이제 주파수 도메인에서 핑크 노이즈 싸서 이렇게 보는 게 제일 간단하고 예, 그냥 그래프로 보면서 판단하는 게 제일 나을 것 같습니다.
So, to, you could say, round off this part of my presentation, in order to trust the test you do, it's also important that you use good high quality test equipment. Because your measurement is not better than the test equipment you do use. So if you use cheap test equipment, you get maybe not so good measurements. Also, we recommend to use standardized equipment. Standardized equipment means you can compare measurements to measurements you are doing in your R&D lab, maybe to production line, to another office somewhere else. You're sure that they are all using equipment that has the same characteristics. And last thing we recommend is to also calibrate. I often get the question, how often should I calibrate my equipment? And I say, it depends. It depends on your use of the equipment. Are you using it in an R&D lab where it's only being used once in a while? It's only being used by very, you could say, skilled people who are used to the equipment and take very good care of the equipment? Or is it being used on the production line where the operators are not always, you could say, they don't always know how delicate the equipment is, and they might abuse it more than normal. So in the production line, you need to calibrate more often. Often 1, 2, 3, 4 times per day, just to make sure your setup is measuring correct, which is very important. But in the R&D lab, it might be once a week, once a month, once a day, again, depending on either your, you could say, feel for it, or maybe you have some policy in the company that you have to calibrate, but it's not as often as on the production line.
우리가 그 측정 장비를 쓸 때는 싼 장비에서 쓸 때 좋은 정답은 나올 수가 없습니다. 돈 투자한 만큼 더 좋은 성능을 볼 수 있는 거고요. 그리고 반드시 이제 국제 표준을 따라야 되는 거고, 그리고 아까 이렇게 자꾸 강조하시는 게 캘리브레이션 이야기하는 겁니다. 캘리브레이션은 매 측정 때마다 하는 게 최고 좋죠. 특히 프로덕션 라인에서는 매번 하는 게 좋습니다. 왜냐하면 프로덕션 라인 같은 경우는 특히 비싼 그 마이크로폰 이런 거 쓰지 않기 때문에 언제 어떤 일이 벌어질 줄 모르고, 그게 틀어져 버리면 엄청나게 많은 회사에서 비용을 지불해야 될지도 모르기 때문에 프로덕션 라인에서는 오전 오후 계속 캘리브레이션해서 써야 된다고 볼 수도 있습니다.
So the reasons for mentioning these things is also that when you are testing on the production line, again, if you use good high quality equipment, you can make sure you avoid approving bad parts, and you definitely don't want to send parts that are not fulfilling specs on the market. The customers don't like that. And you can also risk actually rejecting parts that are fulfilling your specs because the equipment is not giving you the right result. And also, by using high quality equipment, you can minimize downtime on the production line. Production line downtime is expensive. So often the money you saved on equipment are spent on other things like downtime on the production line. So the cheapest solution to test your product is not always the cheapest, because you might end up spending more money fixing it afterwards. So this concludes part of my first part of the presentation. The next part will be about some new developments we have done. And like Nicholas mentioned, we have a very wide range of equipment for testing this, the widest on the market. But we constantly add, you could say, new things. We try to always be in the front, designing the latest new ear coupler that can be used even better to test the equipment today. So what we talk about is the next generation of ear simulators. So why do we need a new generation of ear simulators? Both because historically headphones were not so much used for listening experience. It was more for communication or hearing aids where you had limited, you could say, need for high frequencies, or the quality was not that important. But today the consumers or the customers demand very high quality of their listening devices. That also means that there's an increasing demand. More people are willing to spend a lot of money on headphones today. 20 years ago, people would spend very little money on headphones. They usually were happy with the headphones supplied with your phone or with your little iPod. But today they are willing to spend a lot more money on high-end headphones. Also, there are some technological shifts in the business. In the past, headphones were passive devices, just speakers, drivers that gave you music. But today they can include Bluetooth, they can include ANC, noise cancelling circuits, they can include even some monitoring of your, you could say, heart rate, pulse, even if they're sitting in your ear, steps. So they come with a lot of features today. So the need for tests have changed. A big company who do chips, noise cancelling chips, but they also do chips for a lot of other things, Qualcomm in US, made a survey where they asked, I think, about 4,000 people, what is the most important thing when you buy a headphone? What are you focusing the most on? And the two, you could say, winning answers was sound quality and new features. So sound quality has a very high ranking when people pick up their headphones. They like the sound to be good, but they also like new features. And of course, that's what we all try to put new features in our products. So the goals for next generation of ear simulators: better high frequency measurements. If we could do very repeatable measurements, at least up to 20 kilohertz, maybe even higher. Better low noise measurements, if possible, so we can measure the electrical noise of devices that have noise cancelling circuits or Bluetooth in. We would like it to also give us better repeatability, so we can repeat the measurements we do. And optimal would also be that it was backwards compatible, so we can still compare our measurements with older measurements we did yesterday. And we would like the solutions to be based on well-known standards.
지금 넥스트 제너레이션이라고 이야기하는 이 부분이 왜 지금 이야기를 하냐 그러면요. Would you please show previous page? Okay.
Yeah, coming up.
저기 베럴이라고 적혀 있는 말은 지금 계측 장비가 다 문제가 너무 많은 거예요. 지금 이분들이 팔아먹고는 있지만 이게 굉장히 문제가 많기 때문에 첫 번째 고주파수를 못 잰다. 10km 이상은 못 재게 돼 있고요. 두 번째는 ANC하고 블루투스 성능을 못 잽니다. 정확하게. 여러 문제 때문에 이제 그 이야기를 할 거예요. 세 번째는 재현성이 없어요. 잘 때마다 다르다는 거지. 지금 굉장히 많은 문제점을 내포하고 있고, 그래서 이제 넥스트 제너레이션 해가지고 나온. 그러면 옛날에는 왜 이걸 쓰느냐? 뭐 이런 것에 대한 요구가 별로 없었기 때문에. 지금은 여기에 대한 요구들이 많아졌기 때문에 이런 기능을 넣을 수밖에 없는 그런 시기가 됐고요. 그래서 이런 새로운 신제품을 이렇게 내게 된 겁니다. 그럼 왜 이렇게 낸지에 대해서 이제 하나씩 둘씩 따져보도록 하겠습니다. 오케이?
So the first device I will introduce to you is our new high-resolution ear simulator. We stated up to 20 kilohertz, but I will also talk about what happens after 20 kilohertz. In order to understand what it is we are, you could say, trying to do better, I go a little bit back and start with a presentation of what we have today, the, you could say, traditional standard 711 coupler. It was designed many years ago, and that's also why we think we need to, you could say, come out with next generation. And what we tried, you could say, to fix in what we call our high-resolution coupler is the limitation in the frequency range, where that coupler is, you could say, limited to about 10 kilohertz upwards. And according to standard, it only has, you could say, a well-defined spectrum up to 10 kilohertz. And after 10 kilohertz, it's fairly, you could say, undefined. And what we are looking at above 10 kilohertz is actually a very high resonance, high peak here. And trying to do measurements when you have these very, you could say, sharp edges here is very difficult, because just changing a little bit in frequency changes the dB levels a lot.
기존의 커플러는 10kHz밖에 못 쟀습니다. 왜? 이게 재밌는 거는 이게 이어폰, 헤드폰의 역사는 보청기 때문에 나온 거거든요. 거기서 저희 만들었기 때문에 그 기준은 8kHz까지만 보면 됐기 때문에 모든 이어폰, 헤드폰을 재는 장비의 대부분들은 10kHz 이상을 아예 보질 않았습니다. 그게 지금까지 온 겁니다. 지금 이제 고쳐보려고 하는 겁니다.
So if we again just briefly sum up the specification according to the IEC standard, it specifies some narrow tolerances up to 10 kilohertz. We shown here by the, you could say, red lines. And it also specifies that the coupler should have some kind of resonance around 13.5 kilohertz, but with a fairly wide tolerance of 1500 hertz, plus minus. That means that this resonance peak can move up and down in frequency quite a lot, making the measurements up at high frequency even more difficult to do. Again, to understand how, you could say, we improved, I will go a little bit backwards and explain how the actual ear simulator obtains this frequency response. If we look at a cross-section of an ear simulator, the 711 coupler, it consists of a, you could say, main volume, which simulates part of the ear canal. But it also has these little side volumes connected to the main volume with little air canals. And each of these volumes have influence on the response over here. The way we measure this response, we see over here on the right, is by placing a sound source here at the reference plane, and then record with the built-in microphone here, you could say, simulating the eardrum. The little side volumes we have is what gives the curve this little bump down here at this area. And the main volume is what's causing this half-wave resonance. So it's simply half a wave with this length. So this length is about 12 millimeters, gives us this half-wave resonance.
이 그래프에서 보면요, 저게 뭐 지금 아까 빨간 거 위아래로 표시된 거 있죠. 국제 표준에서는 저 안에만 들어오면 되기 때문에 그 다른 것들은 맞출 필요가 없습니다. 그래서 13.5kg가 얼마나 많이 튀든지 아무 상관이 없습니다. 어쨌든 거기에는 표준이 안 들어있기 때문에. 그래서 저 빨간 선 안에 들어오기 위해서 13.5kg에다가 피크를 만들어서 이렇게 올라가야 되니까 저렇게 기본적으로는 만들고요. 그럼 사람이 저렇게 피키하게 저렇게 13.5를 저렇게 됐나? 전혀 그렇지는 않습니다. 그래서 이거 자체가 굉장히 모순이에요. 지금 지릴리 커플러를 재면 그 고주파석에서는 전혀 틀린 응답이 나오고 있는 거고요. 그 다음에 지금 왜 1kg에서 붕 솟는 것들은 사람이 아까 봤지만 고막은 안에 내이가 더 들어 있습니다. 한쪽에 공간이 또 있거든요. 그런 것들을 모사해 주기 위해서 1kg에서 붕 뜹니다. 그래서 이어 시뮬레이터를 반드시 캘리브레이션을 할 때는 1kHz 톤을 절대 쓰면 안 됩니다. 250Hz 톤을 써야 돼요. 저 이유 때문에. 예. 예. 오케이.
Okay. So now we understand how you could say, measure the response of the ear coupler, and also that the resonance is measured right at reference plane in here, right at the entrance of the coupler. But what often happens is that we add, you could say, extra ear canal. So the ear canal will end up being longer than just the main volume inside the coupler. And that will actually affect this resonance. That resonance will move down in frequency when you have a longer ear canal. So what can happen is that instead of having just one resonance, we now have a picture with two resonances, one being the half-wave resonance that moved down in frequency with longer ear canal, and now suddenly we can also see the full-wave resonance. So not only do we have a resonance with a very, you could say, sharp peak here on the picture, but we can also have that resonance moving and even having the full-wave resonance being visible, and that will, you could say, complicate your high frequency measurement even more than just one resonance.
지금 그 나중에 이어폰을 여기 위치까지 놓고 만약에 된다고 하면 이게 13.5의 피크가 뜨게 되어 있습니다. 그런데 절대 이런 이어폰은 없습니다. 아파 죽습니다, 귀가. 귀가 허벌창까지 크고 막 깊이 넣으면 여기까지 들어가는데요. 이거는 보청기 할 때 넣으라고 여기까지 넣으라고 되어 있습니다. 그런데 어쨌든 여기 기준이 DRP라고 여기 정해놓은 거거든요. 근데 사람은 이쯤에 있는 거죠. 이게 좀 깊이 들어가는 좀 여기 이렇게 위치하게 되는데, 그거에 따라서 이게 이제 피크 위치가 여기 있던 게 일로 바뀝니다. 13.5가 8kg까지 떨어지고 7kg까지 떨어지고 계속 이렇게 바뀌거든요. 이게 이제 여기서 여기 마이크로폰 여기서 여기까지 오는 이제 반파장 공진인데요. 이게 밑으로 내려오면 요 사이에 이제 전파장 공진인 그 한파장 공진이 이것도 같이 보이게 됩니다. 그래서 실제로는 피크가 이거는 2분의 1 파장 공진, 전파장 공진이 같이 생기는 거예요. 근데 이 위치는 이게 이어폰의 삽입 위치에 따라서 이제 다 바뀝니다. 다음.
So just to understand how this, you could say, extra ear canal length, how sensitive it is to adding extra ear canal, we did a test where we moved the sound source. We have a sound source here, and we just moved it away in different steps. So just taking it away 2 millimeters will change the resonance, like you can see over here. And if we start adding, you could say, more length to the ear canal, we get a picture that looks a little bit like this. So you can see that the resonances move down, and you suddenly also can see the full wave resonance, making it very important to have, you could say, correct insertion depth of your headphone, especially if it's in ear every time. But also, again, having lots of, you could say, sharp edges on the resonances that can complicate high frequency measurements a lot.
이거 위치에 따라서 이렇게 그 피크가 굉장히 이제 이 전파 피크가 작아지면서 점점 커지게 되는 거죠. 이것 때문에 너무 이렇게 Q 값이 너무 크다 보니까 삽입 깊이에 따라서 특성이 너무 팍팍 바뀌어 버리는 거예요. 예. 그런데 실제 사람 귀가 이렇게 피크가 있냐? 절대 그렇지가 않습니다. 이렇게 만든 이유는 10kHz 이상은 아예 우리는 보지 않았기 때문에 막 만든 거예요. 그래서 그냥 쇠로 가지고 대충 깎아가지고 만들다 보니까 팍 솟았거든요. 근데 사람의 귀는 알지입니다. 고만 같은 경우에는 굉장히 플렉시블한 소재지 않습니까? 그래서 이렇게 댐핑이 크지 않습니다. 그래서 삽입 깊이에 따라서 그렇게 많이 안 바뀌어요. 이렇게 피크처럼. 그게 기존에 갖고 있는 이어 시뮬레이터가 제일 큰 문제점이었어요. 삽입 깊이에 따라서 특성이 완전히 너무 엄청나게 바뀐다는 거예요.
So, the new high-resolution ear simulator, we set out to, you could say, update the existing ear simulator. We wanted it to be backwards compatible, so mechanically you could say exchange it in your existing setup. But we wanted to improve the high frequency response, so we didn't have to fight with all these sharp resonances. By doing that, it would give you a much more, you could say, repeatable result up at high frequencies. And as a little side effect, which I will explain more in detail later, it also improved the measurement of THD and Robin bus. So on this picture, we can see what we did. We have the standard 711, the traditional one with the sharp peak, and we just managed, you could say, to dampen that peak. Very simple solution, but much more difficult to actually do. And this means that we now have just a, you could say, tiny little resonance here instead of this very high Q resonance. And not only did we dampen the peak, but we also, you could say, managed to extend the tolerance. Before there were no tolerance above 10 kilohertz. If we look at the previous one, we can see that the IEC tolerance stopped here at 10 kilohertz.
그러면 지금 이게 새로 나온 커플러인데 당연히 아까 이야기한 것처럼 좀 더 사람하고 더 모사해주기 위해서 13.5kHz의 피크를 많이 죽여놨죠. 그럼 진작 이렇게 만들지 왜 옛날에는 저 개떡같이 만들어가지고 이 골치 아프게 했습니까? 그런데 옛날에는 뭐 10kHz 이상을 아예 볼 필요가 없었기 때문에 그냥 쇠 깎아가지고 그냥 막 만든 거예요. 지금까지 이렇게 쏘은 거고 아무 문제가 없었거든요. 그런데 이제 음악을 듣는 시대가 왔고 하이레즈 시대가 하이 레졸루션 오디오를 막 들어야 되기 때문에 이제 와서 이제 이게 문제가 대두가 됐고 이제 와서 이제 이 부분을 좀 죽이는 게 좀 더 현실에 가깝다고 이야기가 나오고 이렇게 함으로써 좀 더 이렇게 삽입 깊이에 따라서 편차도 줄어들고요. 사람하고 좀 더 나중에 이제 이거 측정 그래프를 보면 사람이 듣는 그래프하고 좀 더 가까워지는 거예요. 그래서 옛날에 옛날 711 커플러를 재가지고 DF, FF, EQ를 해가지고 보면 고주파수 되게 이상했거든요. 저렇게 안 들리는 것 같은데 다 여기서 기인된 겁니다.
So as mentioned, we managed to extend the tolerances, which means that now your measurements are much more repeatable because the sharp resonance is not there anymore, and also the tolerances are now extended. So you can do from coupler to coupler, and in the same measurement, you can rely on a much higher repeatability of your measurement. Response below, you could say, is still fulfilling 100% the IEC tolerances, and even up here we still have a resonance. We just managed to dampen the resonance. So the new coupler here is still fulfilling the IEC 318 standard, just making it much easier for you to do repeatable results. If you remember this picture, this is how it looked with the traditional coupler. We had all these very high Q resonances moving with ear canal length. With the new coupler, we almost removed all these resonances, and also the levels are, you could say, much more stable at each resonance. Again, to help you do repeatable measurements at high frequencies.
지금 이제 깊이에 따라서 이제 그 차이는 생길 수밖에 없는 건데 어쨌든 길이에 따라서 이제 공진이라는 게 들어가기 때문에 하지만 이게 굉장히 Q 값이 작고 넓고 피크가 에너지가 적기 때문에 깊이에 따라서 차이가 굉장히 적고 실제 이 그래프가 이러한 반응이 사람의 어떤 고막에 반응하고 굉장히 유사하게 찾아가게 된 겁니다.
If we look at an, you could say, practical measurements of an headphone just used in the coupler, and do one measurement, the blue curve here is done with the, you could say, standard 711 coupler, and we want to compare it to a measurement done in the new high-resolution coupler. We can see the result up here around 10K is very different. And the ear simulator resonance is what's affecting the measurement at this point here in the old analyzer, and we can see in the new one that ear simulator resonance is almost not there. The next resonance we see up here is the actual resonance of the little speaker, the driver resonance in the headphone, and of course that is still there, but before it was amplified by the resonance in the ear coupler itself or ear simulator, that is now, you could say, also reduced. So you get a more, you could say, realistic and more repeatable measurement where the headphone is not influenced so much, the headphone response is not influenced so much by the high Q resonance in the coupler. I have another measurement here showing the same thing, but that measurement was done by one of our customers, Knowles. Knowles are a big manufacturer of small speakers and drivers, balanced armature drivers. And they did a measurement on a new design they had for a balanced armature. It can be a little confusing to look at this because they did both right and left channel. So we have the green and the blue curve. So these two, the green and the blue ones, are done with the, or measured right and left channel with the traditional standard 711 coupler. And we can see that there are some fairly high peaks. Again, some differences between the two channels, but still there are definitely influence from the coupler. And the red and the, you could say, purple curve are the same measurements done with the new GRAS high resolution coupler. And we can again see here that the resonances we had in the old one, this is halfway resonance, this is full wave resonance, have been dampened a lot, and you get a much more, you could say, smooth curve, much easier to do measurements on. The driver resonance here is not dampened. That is the real resonance of the driver, and that should not be influenced by the measurement. So we only improve around the resonance point of the coupler. So this customer was very happy, and he said it was okay to share the measurement.
Okay,
Yep. Sorry.
이건 그 커넬형 타입 B 드라이버를 사용한 이어폰의 예인데요. 실제 들어보면 이런 거에 비해서 이게 이렇게까지 사실은 많이 튀지는 않거든요. 근데 그래서 이제 그 신형 커플러를, 왜냐 그러면 이거는 아까 2분의 1 파장 공진, 전파장 공진이 큰 피크 때문에 쇠로 그냥 깎았기 때문에 막 무자막자에 깎아서 만든 커플러이기 때문에 나온 그래프였어요. 이걸 가지고 나중에 DF 하나 FF 해주고 그러면 좀 뭐 고주파수가 좀 이상하게 보이죠. 근데 들어보면 별로 문제가 없거든요. 근데 실제로는 보면 이렇게 빨간식으로 하는 게 훨씬 더 주관적으로 들어보면 나중에 이 빨간 커브를 가지고 DF, FF를 먹이면 훨씬 더 이거 좀 내가 듣는 거하고 좀 비슷한 것 같아 이렇게 느껴지는 거예요. Next.
Okay. I mentioned also that removing this high Q resonance in the coupler also helps on your THD measurements. Normally when you do a THD measurement, you would expect that the fundamental would be, of course, very high, and then the different harmonics would decrease by the higher the number. But if you are, you could say, unlucky and your fundamental is a fraction of where you have the high Q peak, instead of having a low level right here at the fourth harmonic, what you would actually see is amplified by the high Q peak in the coupler. So you would pick up harmonics that are looking higher than they actually are in the real world. So it will influence your harmonic distortion. Again, yeah, oh, sorry.
일반적으로 THD 될 때는 5차까지 에너지를 보거든요. 내가 1kg 넣어주면 2kg, 3kg, 4kg, 4kg 원래 만들면 안 들어지는데 그 양이 들어가는 게 이제 왜곡으로 나오겠죠. 그리고 일반적으로 5차까지를 대주는데 이거 아시겠지만 실제로는 이게 내주면 2차, 3차, 4차가 저렇게 작아져야 되는데 저기 임피던스 피크 있지 않습니까? 무책임하게 만든 저 피크 때문에 10kg에서 저 피크 때문에 하모닉스가 이거 예를 든다고 하면 13.5니까 거기에 대한 4분의 1 분수배로 하면 한 3몇 킬로 되겠죠, 그렇죠? 예, 한 3몇 킬로가 THD가 괜히 크게 보이는 아주 이상한 현상이 생기는 거죠. 예, 4차의 에너지가 크게 부스트가 돼서 보이기 때문에.
Again, practical measurement, same customer, same driver. Now we're just doing a THD measurement. The fundamental was 100 dB input signal. And we can see when we again have fundamentals that are a fraction of the two resonances, the THD is measured much higher than it actually is. Again, the green and the blue curve are measured with the standard traditional coupler, and the purple and red are measured using the new high-res or high-resolution coupler 711. Again, a big effect on the THD, and of course, if you are a manufacturer of drivers, you want your THD to be as low as possible. And you are definitely not interested in the measurement equipment adding on to your THD. So again, they saw very good results of this and are very happy with the new ear simulator.
지금 그래프는 THD 그래프고요. 주파 특성 그래프가 아닙니다. 여기하고 이렇게 크게 나온 것들은 아까 반파장 공진, 전파장 공진 있지 않습니까? 이렇게 큰 피크 때문에 크게 나온 건데 이게 진실이 아니었다라는 거예요. 그래서 이제 하필이면 이 주파수인 주파수들이 아까 그게 전파장, 반파장 공진의 피크한 주파수의 어떤 분수배에 있는 부분이라서 크게 나온 부분인데요. 실제적으로 보면 저렇게 크게 튀지가 않는다는 거죠. 네. 오케이.
Just showing the two areas where we have the improvement. So, just to sum up what I talked about, the new coupler comply with the IEC standard, so we are still fulfilling the standard. But you can now measure high frequencies with much better repeatability. You have an improved ability to measure THD and Robin-Boss. Much lower deviation from coupler to coupler, so when you are comparing measurements between two setups, you know that the measurements will be very, very alike due to tighter tolerances up to 20 kilohertz. Yeah, improved repeatability, I mentioned that many times. Backwards compatible, also with your measurements, at least up to 10 kilohertz. You can compare data because they are still fulfilling the IEC. Oh, if you need to repeat, or can I continue?
Continue.
Yeah, okay. So far I talked about what happens up to 20 kilohertz. But I know also that some people are interested in what happens after 20 kilohertz. And it's not like our equipment stops measuring. So if you look at this one, we can see the IEC specification goes up to 10 kilohertz. We have now extended the narrow tolerances up to 20 kilohertz. But what happens if we try to push it even further? So what we did was we did test our couplers, both the, you could say, old 711 coupler and also the new one. And we also tried to, you could say, extend the frequency range even further than what the standard microphone we use in our ear couplers. We typically use a half-inch microphone that starts rolling off after 20 kilohertz, but we also tried to do measurements where we added a quarter-inch, smaller microphone. The smaller quarter-inch microphone can measure very high frequencies, up to 70 kilohertz. So the first curve I show you is a measurement of, you could say, the traditional standard 711 coupler with half-inch microphone, but also a special S version where we introduced a quarter-inch microphone. And the next measurement I will show you is the same measurement, but with the, you could say, new high resolution, or you could say low resonance coupler, so you can see the differences. If we take the first one and take a look at this, the red curve here shows how it looks all the way up to 70 kilohertz when you measure with a quarter-inch microphone mounted in the ear coupler over here. And the blue curve shows what happens when you have the traditional half-inch microphone. And as you can see, after 20 kilohertz, which is around this point here, this is 20 kilohertz, there are still lots of output. Even with the half-inch microphone that starts rolling off, there's still output. Yes, it is, you could say, dampened the higher you go in frequency, but you can even use a half-inch microphone to do fairly good measurements up to 40 kilohertz. Yes, it's dampened, but it's very well-defined roll-off. And that can, you could say, you can get that data from us. But if you really want to go high, we recommend to use the quarter-inch microphone, and you get the, you could say, red curve response, meaning you get really good high output, even up to 70 kilohertz, from a coupler that is only, you could say, defined or well-defined up to 20 kilohertz. But you can still use it up to higher frequencies.
지금 이 그래프가 몇 개 빠져 있는데요. 나중에 이거는 보내드릴 때는 업데이트된 걸 해드릴게요. 지금 그 핸드아웃 자료에는 이 그래프가 없을 겁니다.
These measurements were done with the, you could say, old coupler with the high Q resonance. If we look at a similar measurement done on the new high resolution coupler, we can see that all the sharp peaks are being dampened. Only up here at very high frequencies, we still have some, you could say, high Q peaks. And we believe it has to do not with the, you could say, ear canal length, but more to the diameter of the ear canal. The last curve I will show you show the difference between the two ear couplers using quarter-inch microphones. So the red curve here with the 13 kilohertz resonance, and again double frequency resonance and so on, is the old standard coupler, and the green curve shows the dampened resonance coupler, the high resolution coupler. And by dampening these resonances, you get a much higher chance of getting good repeatable results, even beyond 20 kilohertz. So the equipment can be used also for higher frequencies, although you could say we specified being very linear up to 20 kilohertz only.
여기서 20kHz 이상을 재시려면요 반드시 4분의 1인치 마이크로폰을 사용하는 걸 권장을 하고요. 나중에도 이야기 나오겠지만 매그니튜드 특성도 있지만 위상응답에서 많이 틀어지거든요. 그래서 4분의 1인치 이야기를 계속 하고 있는 거고, 이 4분의 1인치 같은 경우에도 이렇게 댐핑을 시킴으로 해서 70kHz까지 이렇게 잴 수 있는 거죠. 지금 이거는 사람이 듣고 안 듣고 문제가 아니고 우리 제품에 대한 퍼포먼스, 성능을 보여주기 위해서 필요한 데이터이기 때문입니다. 실제로 사람은 40kg, 50kg는 건 들을 수가 없기 때문에. 예.
So this was, you could say, the first coupler I wanted to present to you was the high resolution coupler. The next one is one we did to focus on the very low noise. Again, because devices today, new headphones actually have some hissing noise coming from electronic circuits. So what we did was we took one of our very, very low noise microphones and combined it with a traditional 711 coupler. And that means we can now actually do measurements down to human hearing. So what you hear is also what we can measure. Where the, you could say, traditional coupler had a fairly high noise floor, there were still measurements that would be, you could say, down in the noise floor of the measurement equipment, but you could hear it with your ear. And that enables us to measure these little hissing noise coming from electrical circuits in the headphones. It could either be Bluetooth or it could be noise cancelling circuits in the headphones. And they tend to have a, you could say, quiet shh hissing noise that you can detect in the background. So what we have acquired with this new coupler is that we can actually measure this. I'll speed up a little bit because we're also running out of time, and I have a nice demo where we can show you what this can do. So I will run through this presentation a little bit quick. Okay, this was actually something I should have skipped. I have more details coming a little later.
오케이. 지금 711 커플러는 2분의 1인치 마이크로폰이 들어가 있었어요. 노이즈 레벨이 25dB 이상이면 반드시 나옵니다. 그래서 ANC 이라든지 블루투스의 히스 노이즈, 만약에 백그라운드 화이트 노이즈 같은 게 깔려 있는 거는 절대 측정을 할 수가 없습니다. 내가 비록 무향실에 넣어서 측정을 한다고 하더라도. 그러니까 지금 그 이야기를 하고 있는 겁니다. 그래서 로우 노이즈 되는 마이크로폰하고 그에 대한 이제 프리앰프가 필요하게 된 거죠. 예. 지금 ANC에서 씩 하는 거 못 잽니다. 사람은 들을 수는 있습니다. 근데 측정기에서는 못 잽니다. 그게 웃기죠. 현재 상황이 그렇습니다.
Okay, so again, I'll be a little bit quick, but what we managed to do is, again, we combined the low noise microphone with the coupler. So we now have a very high sensitive microphone mounted in the coupler, meaning we can push the noise floor below 10 dBA, and if you look at it in octave spectrum, it's very, very low, and the demo will show a little bit later. Again, mounting a different microphone, a low noise microphone in the coupler, changes what happens above 10 kilohertz a little bit. Below 10 kilohertz, we are still well within the IEC tolerances, but above, as you can see on this graph, we now have, you could say, instead of having only one peak, the red curve, being the old traditional 711 coupler, we now have two smaller peaks. So it's still not perfect for high frequency measurement, but for very low noise measurement, it's optimized.
피크가 두 개 뜨는데 좀 이상한데요. 저는 어쩔 수 없어요. 로 노이즈 진동판을 만들다 보니까 2개밖에 못 떴어. 하지만 10km로는 정확하다. 그래서 로 노이즈 마이크로폰으로 만든 것들은 ANC라든지 블루투스 이런 거 잘 때 쓰는 거지 하이레드용으로 쓰면 안 됩니다.
So, just to give you a good picture of what's happening here, we can say the blue dotted line here is the hearing threshold of human ear. The red line is the traditional standard 711 coupler noise floor. And as you can see, there's still a big area down here where the human ear can hear, below the red line, where we cannot do measurements because of the noise floor. But the new ear coupler, low noise ear coupler we have done, lowered the noise floor down to, you could say, human hearing threshold. To give you a simple test and show you what happens, what we did was we took our, you could say, mannequin, the head and torso simulator, put it in an anechoic room, and we did a background measurement, background noise measurement, and we did a measurement with the headphones in passive mode, meaning no noise cancelling circuit turned on, and there was no music, meaning no signal to the headphone, just trying to find out what the background noise is. And then finally we turned on the noise cancelling circuit to see if the noise comes up when we turn on the noise cancelling. We still have no signal. And this picture here shows, you could say, the result done in our anechoic room. The, you could say, low frequency part, what happens below 100 hertz, was a little bit polluted by, you could say, noise coming from our office, because the measurements were done in a fairly noisy environment. But if we look at what happens, you could say, above 100 hertz, the blue curve here on this graph shows the background noise measured with the mannequin with open ears, no headphones mounted. The red curve shows similar measurement but with the headphones mounted but in passive mode, meaning no noise cancelling circuit turned on. And the green and the purple are two different stages of noise cancelling. And this shows you the hissing noise we can hear but couldn't measure in the past. So this is not measuring how well the noise cancelling performs. This is measuring the noise of the electronic circuit that generates the noise cancelling. And if we had used a traditional coupler, this is the noise floor of a traditional coupler, we would not be able to see these signals. These signals would be down in the noise floor. But with the new low noise coupler, we can now see the result, meaning we can now measure what you can hear. And as a, you could say, final thing for my presentation, I'll do a quick demo, because we have here in our mannequin here, we have one side being a traditional ear simulator and the other side being low noise. And we can show, using sound check from Listen, we can show you the two different results. And if we are quiet during the measurements, we should actually be able to show you that this pair of headphones have a little bit of noise.
But audio, please explain first and demo next.
Okay.
Yeah, but previous page.
I think he wants the slide.
Oh, sorry, the slide.
If you can.
네,
Yeah.
지금 이거 전원을 하나도 안 켜고 이제 이게 ANC 이런 거예요. 전원을 하나도 안 켜고 하면 노이즈 레벨이 이렇게 낮았어요. 이렇게 낮았는데 전원을 켜는 순간 전자잡음하고 막이는 그 잡음들 있지 않습니까? 그게 확 이만큼 올라간 거예요. ANC를 켜다 보니까 씩하고 뭐가 깔린 거예요. ANC 키면 씩하는 거 되게 많습니다. 그 전자 노이즈가 굉장히 많습니다. 그런데 기존의 커플러 노이즈가 이만큼 때문에 이런 걸 잴 수가 없었어요. 이런 것들을 다 이걸로 나오겠죠. 그런데 이제 이제 이 노이즈 레벨 요만큼 내려놓으니까 요만큼의 노이즈인지 요만큼 노이즈인지 알 수 있게 된 거예요. 지금에서 알 수 있게 된 거예요. 옛날에는 25데시벨 이상으로 이렇게 씩한 것들이 마이크로폰 자체에서 마이크 프리앰프에서 만들고 있었기 때문에 이런 그 히스 노이즈가 만들어진 레벨을 알 수가 없었어요. 그 이야기를 하고 있습니다. 오케이.
Okay, so what we'll do is we'll take these headphones, put them on the keymer here, and first measurement will be in passive mode, meaning no noise cancelling circuit switched on, just passive damping.
지금은 ANC 안 켜고요. 그냥 키를 막고 얼마만큼 그 음이 외부 소음이 줄어드는지부터 볼 겁니다.
And just to explain what you're going to see, we'll need you to be very quiet, which you already are, is we'll see two spectrum analyzers. One will be the low noise is on the left, and then you'll see the right spectrum of the high, actually it's a high res but higher noise floor on the sorry, this is
High noise floor on the right side.
Yeah,
and
high-
noise floor on the
left. Okay, thanks.
Okay.
Yeah.
So what you can see here is the blue curve here is the noise floor at the coupler. It's not measuring any signal anymore. It's the internal noise of the coupler itself or the microphone. Where the green curve is from the low noise side, which gets a much lower signal.
저렇게 차이가 난다. 뭐 이야기. 그래서 근데 이건 하려면 적어도 무향실이 있어야 됩니다. 바깥이 더 시끄러우면 뭐 아무것도 잴 수가 없겠죠. 무향실이 있는 상황에서 내가 ANC라든지 블루투스 있는 것들이 진짜 노이즈가 있는지 없는지 재려면 이렇게 로 노이즈 제품이 반드시 있어야 된다는 거죠.
So now we'll turn on the ANC.
So we will try to switch on the noise cancelling circuit in the headphones and make a comparison between the no noise cancelling circuit and noise cancelling circuit on the low noise
이제는
side.
ANC를 켜서 한번 보도록 해보겠습니다.
I have stored the previous measurement. So, what you can see is the green. So we still have the original noise floor of the regular coupler, and we can also see that in some cases we're getting spikes from the noise cancelling circuit, and we're getting a little higher noise floor with the ANC turned on. We can also see, though, that the ANC is actually reducing some of the background noise because it's very effective at low frequencies but not at high frequencies.
Of course, this is not the best, you could say, surroundings. These measurements should normally be performed in anechoic rooms, but at least it show you the huge difference in noise flow, and that we can actually now measure things that would be happening down in the noise floor and we would not be able to measure before. So this, you could say, concludes my part of the presentation. And I believe we...
Pina?
Yeah.
Pina session? Pina.
Yeah, but we are a little over time, so I think we'll...
5 minutes extend.
Okay.
You can.
Okay, then I do have a little bit more, but my time was actually out, so that's why I kind of said, okay, I'll skip here.
커피
But
브레이크 시간을 조금
Yeah.
줄일게요. 조금 남은 게 있어서 뭐 뿌리를 다 뽕을 뽑아먹고 보내야 되기 때문에 조금 더. 오케이.
okay, so we also, you could say, worked on doing a pinner, which is, you could say, more realistic than what was available on the market. And our standard pinner, for historical reason, came with a cylindrical ear canal, and the ear entrance was circular, so it didn't really look like a human being ear. But it was what was available on the market so far. So what we set out to do was to do a pinner that was much more realistic. And I should also mention that not only was it cylindrical, it was also, you could say, turned into a stainless steel ear canal right after the ear entrance point, and it went straight into the head. No bending or anything. So what we did was a study together with the Danish Technical University, where more than 260 people were 3D scan of their ear canals. And that means that we designed an ear canal now that reassembles a human being much more. Meaning we now include the first bend, meaning the pointing forward in your ear canal, which is normal for human ears. And it goes all the way into the second bend of the ear canal. And also the entrance of the anthropometric pinner now is oval. Instead of being circular, it now is shaped like this, which is more, again, human-like. It is also shaped to fit the ear simulator we already talked a lot about, the 711 coupler, or the 318-4 coupler, same thing. And we also, besides changing the ear canal to be more human-like, we also changed the flex, so it now again also compresses more like a human being.
previous page. 기존 같은 경우에는 이게 귓구녕이 뻥 뚫려 있지 않죠? 이 원형으로 있으면 말도 안 되는 이겁니다. 이렇게 생긴 사람 봤습니까? 이걸 가지고 완전 원통형으로 동그랗게 이렇게 만들어놨어요. 옛날에 보청기 연구할 때 이게 편하거든. 그렇게 만들어놨는데 다음 페이지, next slide. 지금 같은 경우는 이제 실제로 보면 사람이 꺾여서 들어간다는 거죠. 이런 걸 이제 다 모사를 했고요. 그리고 이게 들어가는 귀가 적재 동그랗지가 않죠. 이렇게 타원형처럼 생겼습니다. 이제 그런 것까지 지금에서 좀 정신 차리고 만들었다. 뭐 이렇게 생각하시면 됩니다. 옛날 거는 그래서 이거 꽂으면 안 꼽힌다. 이게 잘. 다 측정하다 보면 쑥 빠져버리고 이렇게 돼 있었어요. 근데 지금은 이제 좀 잘 꼽힙니다. 그리고 이 귓바퀴의 경도도 지금 귀하고 좀 더 가깝게 좀 더 플렉시블 하고요. 옛날에는 굉장히 딱딱해가지고 누르면 동전 넣으면 통 튕겨 나갈 정도로 탁 이렇게 되게 딱딱했습니다. 얘가. 오케이.
So what we, you could say, tried to do was to simulate a real ear canal. This shows a cross-section of a human ear, and as you can see, the ear canal is not a straight line into the head. It actually bends forward in the beginning before the ear canal goes more straight line into the head. And that's of course also why when you design in-ear phones, you need to make them fit something that goes forward, because that's how human heads are in real life. They are not an ear canal that goes straight into the head. So by changing the design, we also, you could say, improved the actual fit in the ear, reducing leakage when you are trying to you could say, fit the headphones in the old pinner. It was very difficult not to have leaks. With the new one, it's much easier. And that means you can do your test much quicker.
특히 ANC 측정할 때 같은 경우에는 리키지가 이렇게 기가 잘 꼽히지가 않으면 쑥 빠져버리고 이러잖아요. 그럼 리키지가 심해져 버리면 ANC 측정할 때 정말 정확하게 측정은 안 됩니다. 그래서 뭐 못 빠지게 테이프로 붙여놓으면 그것도 웃기지 않습니까? 이 테이프로 못 빠져나오게 이렇게 해서 측정을 했었어야 됐어요. 지금도 아마 그렇게 하고 있을 겁니다. 그래서 이제 새로운 이 깃바퀴가 새로 나온 거예요.
So if we try again to compare old with new, what we did was a simple test. We asked one of our technicians to do 20 measurements on the same, you could say, setup, using the same headphone. So what he did was just put in the headphone, do a measurement, take it out, put it back in, do a measurement, and then compare all these measurements. And as you can see, at low frequencies, we got a lot of leakage. It was difficult to get repeatable measurements every time.
저주파수에서 차이가 저렇게 많이 난다라는 거죠. 계속 빠지기 때문에.
So very difficult with leaks. Up at high frequencies, there are some changes. You can see this peak right here is actually the resonance peak that moves a little bit up and down with insertion depth.
계속 빠지기 때문에 삽입 깊이도 차이가 나서 고주파까지도 저렇게 계속 차이가 나버리는 거예요.
If we do the same thing with the new improved pinner, the new more realistic pinner, we can see that the low frequency response is much easier to obtain. It's much easier to get a good sealing, good fit. High frequency changed a little bit again because the insertion depth is more well defined now. But it's not, you could say, the big improvement is definitely at the low frequency part and sealing. I also mentioned that the actual compression of the ear was changed. This picture here on the slide shows that we have one side with an old type pinner, which is a little bit harder and more difficult to flex, and the other one is softer and more, you could say, human-like again. On the old one, again, with on-ear parts and even around ear parts, it could be difficult to get good sealing. Where the new one, because it compresses more, it also gives you a better sealing.
이렇게 이건 옛날 거고 지금 건데요. 이게 실제로 보면 이렇게 되거든요. 실제 사람 귀를 보면 이렇게 되면 ANC 잴 때 정확하게 측정이 잘 안 됩니다. 뭐 그냥 일반 이어폰도 그렇지만 특히 ANC 잴 때 같은 경우에는 성능이 많이 차이가 납니다.
So again, we did a similar test like before, where we, you could say, mounted the headphones and tried to get good seal both on the old one and the new one. With the old one, again, we see a fairly big spread at low frequencies, difficult to get good sealing. And with the new one, we have a much better improved response at low frequencies. So not only for in-ear parts, but also for on-ear and over-ear parts, it's an improvement using the new pinner.
깃바퀴 위에 올려서 듣는 헤드폰 같은 경우 이렇게 큰 차이가 더 많이 보여요.
So just a quick summary of my whole presentation. High resolution ear simulator can measure high frequencies with repeatable results and much lower deviation from coupler to coupler due to the tolerances being extended. And we also got the improved ability to measure THD. And we managed to keep the frequency response within the 318-4 limits or the 711 coupler limits. Low noise ear simulator, we can now measure down to human hearing threshold. It enables us to measure the noise of, you could say, today's headphones or modern headphones. Again, frequency response up to 10 kilohertz is within the IEC specs. So again, we managed to get the backwards compatible results. The new anthropometric pinner huge benefits for in-ear parts to get much better sealing and much better reproducible results. But we have also seen that for circumall and supraall, we have big improvements.
제가 지금 그 그라스의 스폰서를 받아서 이런 제품들을 다 써보고 있는데요. 이거는 굉장히 약간 노이즈가 작다지 않습니까? 그럼 단점은 굉장히 그런 노이즈를 작게 하기 위해서 고감도로 설계를 했어요. 고감도로 설계를 하면 증폭을 많이 안 해도 되고, 증폭을 안 하면 노이즈가 당연히 적겠죠. 그래서 이게 그렇게 되어 있는데, 대신에 이제 큰 소리를 못 재요. 감도가 높다 보니까. 그래서 110dB 이상 되는 소리를 잴 수 없기 때문에 일반적인 이어폰, 헤드폰 측정할 때는 못 씁니다. 그래서 일반 헤드폰 측정할 때 이걸 하시고요. 이거는 ANC라든지 로우 노이즈를 해서 뭐 서킷에 관련된 히스 노이즈를 내가 측정해야 될 필요가 있다 그러면 이걸로 쓰시고요. 그래서 결론이 뭐냐? 두 개 다 사라는 겁니다. 하이레즈도 사고 로우 노이즈도 사고. 이거는 반드시 내가 헤드폰 개발하시는 분은 반드시 있어야 되는 부분입니다. 그러면 이 세 개 다 사셔야 됩니다. 오케이.
So, as mentioned, we have always also tried to keep all the solutions backwards compatible, and that means that both the pinner, the low noise, and the high resolution coupler can all be, you could say, used in also older setups because they are mechanically compatible, and therefore it means that you don't have to buy a complete new solution. You can even say, I just need the coupler and I already have a Kima or another setup, and you can replace the coupler. So we have talked a lot about sound today and frequency response of headphones. We are not telling you how your headphones should sound. That's up to you to decide what are the, you could say, best sound of the headphone, and I know Sean Olive will talk about, you could say, the target curve for that later on, but we are just giving you the tools to measure it. So we are not telling you how it should actually sound. And again, I would not tell you that these devices will replace human hearing. It's just a tool that will help you in your development process. And it is the best tools available on the market today. And it will definitely help you do your measurements faster. So it will speed up your process, your R&D process. And it will give you a bit more insight into the behavior of your product, especially at high frequency and very low noises. And hopefully it will also give you results that can be related more to the actual human hearing. So the subjective and the scientific measurements will be definitely more, you could say, alike or correlate better.